So far in this unit, all of the formulas that we've used are formulas you have used before. The area of a parallelogram, the area of a triangle, the area of a trapezoid. You learned all those probably at the latest in 6th grade. We just have added things onto them. This is the first new formula that we're going to have in this unit. So areas of regular polygons is what we're talking about today. Remember that a regular polygon is one that is both equiangular, meaning all the angles are the same, and equilateral, meaning all the sides are the same. So some new terms for you. First of all, the center of a regular polygon is a polygon that is a point that is equidistant from the vertices of the polygon. I mean, equidistant, same distance. You can get that, I think, from the context of this problem. So this would be the center. It's right in the middle. Okay. Notice one thing real quickly is it's not half the way from the top to the bottom in this particular case. It's equidistant from all the vertices. It's actually closer to the bottom than it is to the top. If it was halfway between the two, it wouldn't be in the center. Okay? Then here is another new term for you, and it depends on who you ask as to how you should pronounce it. Apparently, the correct pronunciation is the apothem. Okay? Although I will say that for years I was around people who said it apothem. Okay? I don't care which way you say it. This is the segment from the center perpendicular to a side. We almost always draw it to the bottom. We almost always have a side on bottom, and it's easy to do that. It's just like dropping in an altitude in a triangle. Okay? That is the apothem. It's got to go from the center perpendicular to a side. And then another new term for you is a central angle. But you can, again, kind of get that from context. A central angle is an angle with its vertex at the center. Duh. Central angle. But there's a little bit more to it than that, whose sides pass through consecutive vertices. So, again, so here is the center. X is the center of this figure. An apothem would be right here. And then this angle would be one of several central angles. On this particular figure, which is a, what kind of a thing? A what? More specifically, it's a pentagon. It's a regular pentagon. How many central angles do we have? There's 5 central angles. It's the same as the number of sides. One of the nice things is that makes a quick way to figure out what the measure of the central angle is. Because notice, I'm going to erase all this for just a second, all these central angles added together make how many degrees? 360. So if you just take 360 divided by 5, we get the measure of each central angle is 72 degrees in this particular case. Every figure, depending on the number of sides, is going to have a different central angle. Some of them, for some of you sharper guys, you're just going to memorize it after a while. You'll be like, oh, I've seen enough of those to where I don't have to do this calculation. I just have it memorized. That's good. Okay, I'm not expecting you to write it down every time. I will for a while, at least. probably the whole unit. But if you get to the place where you know, like hexagons, which we do a lot of, where you're like, oh yeah, the central angle is 60 there. I don't even have to think about it. That's great. Now, if we're trying to find the area of this whole regular polygon, where it has n sides, so in this case that's 5, the apothem has a length a, the sides have a length s, we could find that by finding the area of just this one triangle here, and then doing what with it? Yeah, multiply by the number of triangles, which would be 5 triangles. And if you want to do it that way, that is fine with me. I mean, really fine with me. Not just, oh, it's okay, I don't mind. No, there's nothing wrong at all with doing it that way. But there is a formula that is slightly shorter so that you're not doing it in 2 separate steps. Okay? And here's how it works. What we would do is we would take the area of one triangle and multiply by the number of triangles, right? The area of any triangle is half base times height, and the number of triangles is going to be equal to the number of sides. Okay? The base of this triangle is a side of the polygon. We called that S. The height of this triangle is the apothem. We call that A. So I had a student years ago who used this as his formula. He said it was 1/2 SAN. It was 1/2 SAN. I'm like, okay, that totally works. Mathematicians are the either most efficient people in the world or the laziest people in the world, depending on who you want to ask. They're like, that's too many letters. So what they did is they said, okay, if I multiply S times N, the length of one side, times how many sides we have, that gives me the perimeter of the whole figure. So they replaced the S times N with P for perimeter. So this is usually the formula that people will use, 1/2 A times P, where again, A stands for the apothem, and P stands for the perimeter of the polygon. You might want to write that in. I will tell you that when we're doing these, if I ask you, what formula did you use? And you say 1/2 AP, I'm going to ask you, what does A stand for and what does P stand for? Because it's great to know the letters, but if you don't know what they stand for, it's not much good to you. All right. So let's do some examples. For the first one, find the area of a regular hexagon with sides of length 12 centimeters. So we'll draw a hexagon. Typically, if it has 8 or less sides, I draw the whole thing. If it has like 12 sides, I don't draw the whole thing. I just draw the central angle in one of the sides. It just gets too hard. I don't know about you, but I can't draw an accurate nonagon at all, much less a dodecagon. So here we want a hexagon where every side is 12. And as always, when you're making these, one of the mistakes that students tend to make is they make it so small that they can't tell what's going on. Try to make it fairly large. So every side of this is 12 centimeters. Then what we're going to do is, I usually don't draw all the central angles. Again, that whole lazy part. I usually just draw one of the central angles. And we figure out what its measure is. The central angle is going to be 360 divided by 6. Cole, you with us? So that's 60. So this angle is 60. I don't normally draw the 60 on there though because the apothem's going to split it in half. So the apothem splits the side in half and splits this angle in half. It splits this triangle perfectly in half. So each of these angles is 30. And each of these pieces will be 6. So now, what kind of a triangle do I have? Got a 30, 60, 90. And I've got that this side is 6. Which side is this side? Short leg, because it's across from the 30-degree angle. So to find the long leg, multiply by the square root of 3. So this would be 6 square roots of 3. So now I have everything that I need. The area is 1/2 the apothem times the perimeter. So it's going to be half of 6 square roots of 3. And how am I going to find the perimeter?
Multiply 12 by 6.
Yeah, multiply 12 by 6, because every side is 12 and there are 6 of them.
72.
Be 72 times half of 6, which is 3, is 216 square roots of 3 square centimeters. Any questions about this example? Okay, God bless you. So let's find the area of a regular octagon where the apothem is 7 inches. Again, an octagon is about as big a one as I ever want to draw. Once it gets past that, I just draw parts. Yeah, that's close. Just like with the last one, I'll draw in one central angle and figure out its measure. So the central angle is going to be 360 divided by 8. It's 45. And then I'll draw in the apothem. And the length of the apothem is 7. And remember that this also splits in half the central angle. So this angle up here is 22.5 degrees. So although the central angle is 45, we're not going to have 45, 45, 90 triangles here. So I've got the apothem, but I need the perimeter. Well, to get the perimeter, I need to figure out how long the side is. And I can't find the side directly. I've got to find this little piece right here, which is half of a side. Right? I'm going to use this right triangle. I'm going to find this piece. I'll call it X. If you want to call it half of S, you can do that also. So from the 22.5, X is which side? Opposite, thank you. And 7 is adjacent, so we're going to use tangent. The tangent of 22.5 is equal to X over 7. Multiplying both sides by 7, I get that x is 7 tangent of 22.5. So how long is the whole side?
14 tangent 22.5.
Exactly right. Good. 14 tangent of 22.5. And what would I have to do to that to find the perimeter?
Multiply times 8.
Yes, multiply times 8. And to save myself time, I'm just going to write 8 times 14 tangent of 22.5. So then the area is 1/2 apothem times perimeter. So it's 1/2 of 7 times 8 times 14 times the tangent of 22.5. Everybody grab your calculator. Since I turned mine off, I've got to go back and set it back to degrees. Nice thing about it is it stays in degrees unless you reset it, or I think if you change the batteries, it resets also. So just something to be careful of. So 0.5 times 7 times 8 times 14 times the tangent of 22.5. And since it didn't say, I'll round it to the nearest hundredth. Your worksheets almost always say what to round it to. So it'd be 162.37 square inches. Questions? All right. So this next problem, there's actually multiple ways to do the problem. What kind of a figure is that? It's a square. Is it a regular polygon? Yeah. Is it also a parallelogram? So we could use base times height, or we could use 1/2 apothem times perimeter. I'm going to do both just so you can see how they work. So I'm going to draw in the rest of the central angle and figure out its measure. Central angle is 360 divided by 4 is 90. The apothem splits that in half. In fact, it splits this triangle in half. So this is 45. So we've got a 45, 45, 90 triangle. How do we get the legs from the hypotenuse in a 45, 45, 90? Divide by what? Square root of 2. Yep. Divide by the square root of 2. So 6 divided by the square root of 2. We can't leave the square root on bottom, so we'll multiply by the square root of 2 over the square root of 2. So that's 6 square roots of 2 over 2 is 3 square roots of 2. So both of these legs are 3 square roots of 2. So how long is the whole side? 6 square roots of 2. And now we're ready to find the area one of two ways. Let's do it 1/2 apothem times perimeter first. So that's going to be half of 3 square roots of 2 times, what do I have to do to the 6 square roots of 2 to get the perimeter? multiply by 4, and that's easy enough to do in your head. That's going to be 24 square roots of 2. Anytime you have multiple square roots that you're multiplying together, you should group them. So I'm going to group this way. 1/2 of 3 times 24 times the square root of 2 times the square root of 2. What's the square root of 2 times the square root of 2? 2 times 1/2 is 1. So all that multiplies together to be just 1. So I just have 3 times 24, 72 square feet. The other way we could have done it is that area is equal to base times height. What's the height going to be? 6 square roots of 2. So it'd be 6 square roots of 2 times 6 square roots of 2. Again, we'll group these. 6 times 6. The square root of 2 times the square root of 2. That's 36 times 2 is 72 square feet. Certainly nice that it works out the same way. It would be bad if you did it with 2 different formulas and you got 2 different answers. You'd be beginning to wonder, is one of those not valid? Okay, any questions about that example? All right, one more. Find the area if the apothem is 12 millimeters. All right, so again, as always, I'll start by drawing in the central angle. And earlier I was pointing this out. I think you can see it more easily on this, that the distance from the center to here is much bigger than the distance from the center to the middle of the base. The apothem is much shorter than that. I'll figure its measure. The central angle is 360 divided by 3 is 120.
Why did you do 3?
Because there are 3 sides. It's always 360 divided by the number of sides, because that's how many central angles there's going to be. We'll drop in an apothem here. It'll split the triangle in half. So each of these is 60 degrees. And the length of the apothem is 12. We've got a 30, 60, 90 triangle. And we've got the short leg because it's opposite the 30-degree angle. So the long leg, we just multiply by the square root of 3. So that's 12 square roots of 3. And so is this one. So the length of that whole side is 24 square roots of 3. So I can do areas 1/2 apothem times perimeter. So it'd be half times 12 times the perimeter is going to be 3 times 24 square roots of 3. Let's see, that's 72 times half of 12, which is 6. I think it's 432 square roots of 3. But please someone double check me.
Looks right.
There are many things that look right that are not.
Yeah, that's right.
Thank you. Just a quick, by the way, you don't need to write this down, but you could have also done half base times height. You're like, well, how am I supposed to do that? I don't know the height. Well, if we finish this 30, 60, 90 triangle, the hypotenuse would be 24 because it'd be twice the short leg. And that would be this distance. So it'd be half of the base, which is 24 square roots of 3, times the height, which is 36, which should come out to be the same thing. The mistake people make on that is they want the whole height to be 24 because they think that's halfway up, and it's never halfway up on an odd number of sides. If it's an even number of sides, it is halfway up.
All right. I have a worksheet for you.
Just so you know what's coming up, we will have a quiz next Wednesday on area.